Professor Steve Beebe from Southampton University, who will deliver the invited talk on energy harvesting power supplies for electronic textiles.
Thank you for the introduction. So yes, I'm basically going to give you a very sort of a broad overview of our work on energy harvesting and its application in powering electronic textiles. We've been working on the area of energy harvesting since the late 1990s and e-textiles for over 12 years now, and it's an obvious sort of combination to combine these research interests, especially given the challenges associated with powering e-textiles by batteries. So I'm sure you're all familiar with e-textile technology, but just to give you some examples here. So e-textiles is inherently a multidisciplinary topic. Involves textile engineering, electronic engineering, ICT. There are many examples. It's not a new topic. There are many examples out there. So you can see the sort of LED jacket worn by will.i.am there. So that is a very much a bespoke one-off garment, handmade, very expensive. Certainly wouldn't survive washing in a washing machine. There are sort of commercial devices, or examples shown here. So this is a sports bra marketed by Adidas. So this monitors your heart rate, and it has electrodes woven on the inside here. And these are pressure sensing socks here that are used to analyse your gait and improve your running technique, for example. In both these cases, the actual electronic functionality is quite limited. So to actually communicate wirelessly and process the signals, there are electronic modules that snap onto the front here. So the functionality within the textile is quite limited. Within the research domain, you can see other examples here. So this is an embroidered antenna, and this is a glove that senses the position of the fingers. So our work at Southampton has... Our work at Southampton has taken two approaches to developing e-textiles further. So the first is to actually print active materials onto a textile. So there are lots of challenges which I'll talk about later in working on textiles, but materials certainly have to be flexible and low temperature. And we've developed a range of inks that can do this. I don't know if I can get this to work. Yes, so this is electroluminescent ink, and there's just a display there. And this is an interactive blind, which basically interacts with the user. So it's got a proximity sensor. As you bring your hand close, it does various things depending on whatever you want to do. So it lights up, it plays some music, and there's a thermochromic ink there as well. We've also looked at improving the level of integration of the electronics within the textile. So this builds upon the sort of flexible circuits that Nico showed very briefly this morning. So we take very, very long, thin, flexible circuits. We're working with very, very small chips, ultra-thin chips where possible, and miniaturizing the size of these flexible circuits, and basically getting them down to a size where we can put them inside a yarn or weave them directly into a textile. And what we've done is we've got a patent-pending packaging process that encapsulates the dye, and it's a process that adapts to any topology of the circuit. It makes this much, much more robust. So these can withstand thousands of bending cycles, hundreds of thousands of twist cycles, and well over 50 wash cycles. So any circuit we put into the textile is basically ruggedized and practical. However much you integrate the electronic functionality or expand the functionality, at the end of the day, we still have to use batteries, and these are a real constraint. So, these are rigid, they're bulky, they're not compatible with textiles, the feel of the textile, the flexibility, etc. And the use of these sort of battery housings, for example, they're sources of failure as well. And you certainly can't wash batteries, so they are a real hindrance. So there really is a strong motivation to try and move away from battery powering. So what I'm going to talk about is a range of energy harvesting techniques we've explored at Southampton, from low temperature piezoelectric inks, ferroelectret materials, triboelectric energy harvesting, spray-coated photovoltaics on textiles, wireless power transfer, and fabric supercapacitors. And everything that I present here has been developed specifically for use on textiles. Now, I know most of you people out there are working on flexible, obviously, electronics and devices, and typically with plastic substrates. Well, plastic substrates are great compared to textiles. So textiles are an absolute nightmare. They are rough, they're porous, they restrict the processing temperatures, etc. So they impose real constraints on the technology, whatever it is you're trying to develop. So I'm not sure how familiar you are with energy harvesting as a topic, but essentially it involves capturing ambient energy present in the environment and using energy harvester to convert that into electrical energy to act as a localized power supply to replace or augment batteries. So it's identical in principle to renewable energy, such as big wind turbines, but the power varies by many orders of magnitude. So wind turbines is megawatts, energy harvesting is typically micro to milliwatts. And typically it's employed in this sort of system down here. So you have your harvester, you have some form of power electronics, and they're co-designed to maximise the efficiency of the extraction. There's some form of energy storage to act as a buffer to store up the energy, and then you have your application electronics, which draws upon the energy reservoir, wakes up periodically, does its thing, and then goes back to sleep. So that's typically the way energy harvesting systems work. When it comes to the actual energy sources, with regard to textiles, we typically think of textiles as wearable applications, but textiles are actually used in many different applications: agriculture, architecture, marine environments, etc. So there are many different opportunities for energy sources. There's obviously mechanical energy, light energy, and thermal energy, and I'll talk about the top two. We have done some work on thermal energy harvesting, but it's the least advanced of what we've done. So I'll just focus on the others, and I'll touch upon wireless power transfer as well. So capturing mechanical energy. The most obvious way of doing this is to use piezoelectric materials. So these are very nice, smart materials. I'm sure you're familiar. If you squash them, they generate electrical energy. So they're ideal for sensing and energy harvesting applications. Typically, piezoelectric materials are rigid ceramics, so that again is incompatible with textiles. So we have to develop the material into a flexible, low-temperature processable form, such as we see here. There are ferroelectret materials, which I'll introduce as well. These are nice, soft, compliant materials that they look just like a piezoelectric material, but the mechanism is very different. And there's also triboelectric energy harvesting, which I'll briefly touch upon. So when it comes to piezoelectric, we did look at PVDF as an obvious sort of polymer approach for this. However, the so-called printable forms really aren't very printable. They're horrible to work with. So we developed our own composite ink, where we took a blend of piezoelectric powder of different particle sizes, mixed it with a very small concentration of silver nanoparticles, and mixed this with a suitable polymer into a composite ink. It's very nice to print. We typically print that between two silver electrodes, making a sort of capacitor sandwich structure. And then if you really want to go all the way and make the best possible performing material, you can do this isostatic pressing process, which adds probably about 10% to the performance of the material, but not really practical. But in summary, we achieved a level of activity. So piezoelectric materials are often characterized by their D33 coefficient of nearly 100. So we've got 98 picocoulombs per Newton compared to PVDF, which is around 30. So we made a big improvement on the level of activity. Plus, this is really nice to work with. And then, of course, we want to know how good is it as an energy harvesting material. So we built some rigs to sort of cyclically bend and compress materials, etc. And what we find that despite the activity of the piezoelectric material, the amount of energy actually captured is quite low. So it's in the order of tens of microjoules per bending action or compression action. And this highlights another challenge with textiles in that it doesn't couple mechanical energy into the piezoelectric film very effectively. Textiles are designed to be compliant and comfortable. That's why one of the reasons why we wear them as clothes. So you don't have to put much work in to move a textile. You don't get that much energy out. So it's an obvious sort of connection there. So to improve the performance, and especially in compressive applications, we looked at ferroelectrets. So as I mentioned, these appear like a piezoelectric. If you squash them, you get electrical energy out. But inside the material is a series of voids. And once the material is charged, you get charge trapped across the surface of the voids, which form these electric field dipoles within the material. And if you squash it, you get a net dipole moment across the entire material, and you get a voltage signal and charge flow around the load circuit. These are commercially available in the form of these foams here. So this is a polypropylene foam here showing the voids. Or you can engineer the voids. This is using PDMS, something we did a few years ago. In both cases, they're very soft, very compliant, very stretchable, and they're ideal for human and wearable applications. So we looked at the commercially available ferroelectret foam, and we used this in a compressive application based on a shoe insole to start with. And we coupled this with a simple power conditioning circuit and a capacitor to store the energy. And we basically charge up the capacitor with a few steps, and then you find you've got enough energy in the reservoir to do quite a lot of things. So we, for example, did a wireless self-powered pedometer that you could walk around and run, etc. And it's more accurate than a Fitbit, so less than 4% error just walking, and 0% error if you're running. We also did an indoor version for localization, so as an ambient assisted living application for locating people within a house, just broadcasting a signal every other footstep, just to recognize where people were in the house. That's all very well, but to get that level of power, which I think is 150 microjoules per step, we had to build up the layers of the commercial ferroelectret. So we thought we'd investigate an alternative, easier to fabricate approach. And here we'd basically take a FEP film with an aluminium electrode and basically sandwich these together with a foam insert. Now I've shown it as a sort of discrete foam insert, but in reality that foam could extend all the way along, and you can replace the foam with a textile. The foam insert or the textile is essentially acting as a mechanical soft spacer. So if you compress this, the textile or the foam compresses and you get the ferroelectret effect. And with this you can get a D33 of well over 1,000. So it's many times more active and responsive than the piezoelectric material, for example. So this is, I'll show this in the textile form a bit later on. Triboelectric energy harvesting, I don't know again if you're familiar with this, but essentially it's exploiting the electrostatic effect you get of rubbing dissimilar materials together. So I'm sure you're familiar with rubbing a balloon against a jumper and charging up the surface of the balloon and sticking it to a wall, for example. So you can use the same sort of charging principle with different materials. So different materials will charge differently depending upon the nature of them. So you have materials with a positive affinity that will become positively charged, or negatively charged, depending on the material you're rubbing them with. And here we've got, actually we're combining positive and negative materials, so this is nylon and PVC, and then combining that with an IDT textile electrode here, and when you rub these, the top surface along here, basically you generate electrical energy, which should be shown in this video here. So this is the standard sort of triboelectric demonstration of lighting up LEDs. So from an energy harvesting point of view, it doesn't really tell you how much energy you get, but it kind of looks quite pretty. So that's around 100 LEDs lighting up, for example. So, from an energy harvesting point of view, we want to quantify the energy more accurately and look at the different textiles, for example. So we've looked at cotton, silk, nylon is the best combined with the PVC, and we're getting 80 microwatts typically out of that sort of application with that sort of stroke range or amplitude range. It does depend upon the velocity, not so much on the force, so the force isn't so important, it kind of levels out. But a very, very promising approach for energy harvesting with textiles, because there are many applications where textiles are typically sliding against each other. So moving away from mechanical energy, looking at photovoltaic. So we were thinking of maybe not just wearables, but other applications in architecture, for example, where there are large surface areas of textile available. And it would be great if we could functionalise the surface of the textile with a photovoltaic without hopefully affecting the properties of the textile. So that was the goal. And obviously there are many examples of plastic, flexible photovoltaic devices out there commercially available. So essentially we took these commercially available materials and we tried to apply them to a textile, very naively thinking it would be easy. And it really, really wasn't. So effectively, this device thickness is less than a micron, and the surface roughness of the typical textile is over 100 microns. It's fluffy, it's porous, etc. So you definitely have to use this interface layer to smooth the textile as much as you can. And then we just developed a spray coating process to build the thin film photovoltaics. And using organic materials, we were able to get up to 1.2% efficiency. Again, with all the processing constraints, no more than 150 degrees, for example, for any of the fabrication steps. So it works, but it's not particularly stable, and packaging this is an ongoing challenge to make it stable long term. We also looked at dye-sensitized photovoltaics, so electrochemical photovoltaic cells. Here, well, we had to cheat, really. We couldn't get down to 150 degrees processing temperatures, so we were processing over 300 degrees, so we had to cheat and use a glass fibre textile, and we had to change the interface layer to a liquid polyamide. But if you do all this, it functioned. We achieved efficiencies of about 0.4% with the dye-sensitized, and the flexibility is pretty reasonable. So when we talk about energy harvesting and wearable applications, and e-textiles as well, people often ask, can I recharge my mobile phone as I walk along? And with all the techniques I've talked about so far, not really possible. So we looked at inductive power transfer, and this isn't strictly speaking energy harvesting because you are broadcasting energy and deliberately picking it up. And it's the same sort of technology as you have with your electric toothbrush or your mobile phone now with charge pads. If you operate the system, so you have two coils, a transmitter and a receiver, if you actually operate these at resonance at a particular frequency, you can extend the range and the efficiency of the transfer. So we've looked at basically textile coils and how well they can be used in this resonant mode to increase the power efficiency and the amount of energy you can transfer. So we looked at printed coils, embroidered coils taking a sort of silver-coated yarn, and then we looked at overstitching. So with many embroidery machines, you have two thread paths, and you can put a conductive standard multi-wire Litz wire in the bottom conductive thread path and overstitch with the other thread path. So the machine will very quickly make this coil pattern for you. And we've compared the various parameters of these coils, and this overstitch approach is the best. We've put this onto, for example, a chair, so this might be your favourite chair at home, and if you sit down there and you've got a corresponding coil on your clothing, for example, you can certainly charge your mobile phone, so we demonstrated that. The latest thing we're doing is transferring this on just to a bike as another use case example where you have a coil on the palm of your hand on your cycling glove and a coil on the handlebar, and you can recharge your wearables and your e-textile devices as you cycle along. And the efficiency of that, we've looked at various arrangements of where you put the electrodes, on the back or the front of the hand, for example, and we get transfer efficiencies of up to 80-85%. So that's the energy harvesting or energy capturing point of view. Looking at storing that now, so again, obviously we wanted to avoid batteries, so the obvious approach here was to look at supercapacitors. And fabrics, because of their porous nature, actually form a very good mechanical framework for making supercapacitor electrodes. So what we want to do is basically add a carbon material here which has a very large effective surface area, and then add an electrolyte and make sure those two electrodes are separated and you can form a supercapacitor. And this is how all supercapacitors are basically structured. We do this by making up a very low-cost carbon ink based on just activated carbon with a blend of carbon black to reduce the resistance a bit. And then we use a spray coating process, so we control that spray coating process so that the ink or the solution only is absorbed a certain depth into the textile. And if you do that from both sides of the textile, you can leave a region uncoated at the centre, and that acts as your separator. And using this process, you can take any standard textile and basically make it into a supercapacitor. And in terms of performance, it's very effective. So it has an aerial capacitance of 49 millifarads per centimetre squared. And the cyclical efficiency is excellent as well. So this just shows a CV plot after one cycle and after 15,000 charge-discharge cycles. So less than 1% variation. So it behaves very, very well. So the obvious thing to do then is to combine the two. So the energy harvesting with the energy storage. And again, this highlights the flexibility and the ability to just take any textile. So that supercapacitor process, for example, we've used silks, we've used polyester cottons, etc. Here, this is a polyester cotton substrate, and we're combining the supercapacitor located there with the ferroelectret. So this is where we've used the textile as that mechanical spacer. And if you compress that part of the textile, you generate electricity and then go through a simple rectifier and charge up the supercapacitor. So this works. We've published this, and we're currently improving it using that circuit technology I mentioned at the beginning to remove this rectifier and actually hide the circuitry in the textile and improve the efficiency of the power conditioning circuitry as well. So just to conclude, there is clearly a need to develop energy harvesting or other alternative power supplies for e-textiles applications, but human applications in general are very challenging for energy harvesting, and certainly doing it in a textile is very challenging. Textiles do not couple mechanical energy effectively to the active materials, but ferroelectret, triboelectric materials do show pretty good promise there. Solar harvesting, that would be great if we can get that to work in a low-cost way onto textiles, but again, technically challenging and further research certainly required. So I think the lowest hanging fruit, as it were, at the moment is probably the wireless power transfer. Just before I finish, just a couple of plugs. So we do, at Southampton, we do run the Energy Harvesting Network, and we are doing our first conference, which is in November. So there are some flyers at the registration desk, but we have half a dozen invited speakers and currently a call for papers out. So if you are working in textiles or just want to learn more about the applications, then please come along. It's subsidised by the EPSRC, so it's a very low cost conference to attend, only the single day for the first conference. And final plug, if you do want to look at any of the materials or try any of the inks we've developed specifically for textiles, then we do have a company selling those materials, so you can visit the webpage. And thank you very much for your attention.
Thank you very much. Very nice talk. Can you just talk a little bit more about the corona polarization of your foams and textiles for energy harvesting?
So on the ferroelectret?
Yes.
Okay, yeah, sure. So yeah, basically we've taken FEP because it's a very good electret material, and we can charge that up to a very high level, and it's very, very stable. So it lasts. That just shows the sort of charge over time. So after 10 or 12 days, that becomes very stable. And if the conditions are right, it will last for years. So the charge is trapped very nicely on the FEP. And then we have basically two sheets of FEP separated by the foam or the textile. And very simply, if you compress them, you're just changing the capacitance between the two charged plates. And it's acting like an electrostatic harvester, so you change the voltage between them. So you've got a fixed charge and a varying gap. And it acts like a charge pump. And it's just, in this case we use polymer foam because we can vary the Young's modulus of the foam and look at the effect of the Young's modulus. But again, like I say, you can replace that foam with a textile and run the textile all the way through, etc. It's very simple, like I say, very simple to assemble.
During the polarization, are you limited by the air trapped inside?
It's polarized. It's poled in a corona, so it's done at air temperature. In room temperature, sorry, we put a corona field very close to it to charge it up. It's fine, no problem at all. Yeah.
Any other questions?
Thank you very much for the very interesting talk. I was just wondering, the inductive power transfer, the textile coil that you mentioned, is there any risk of heating up?
Sorry, can you repeat the question?
I said for the inductive power transfer,
yep.
I was wondering for the textile coil if there's any risk of heat being produced. There's any risk?
No. So it's operated at relatively low currents and it's very safe frequencies. So there's no concerns with regard to human exposure, etc. So it's not RF power transfer where you do potentially have concerns. At the frequencies that the coils operate, there's no concerns. Yeah, it's safe.
Other questions? Yes.
Just a quick one. So most of the, thank you very much for the talk, very interesting. Most of the works are using textiles as a substrate. I mean, most technologies are actually a bit imported from flexible electronics with different things. Do you think that some of these devices could be then evolved into, for example, fiber-based devices or something which, exploits more the form factor of the textile?
Sure. Yes, so there's lots of examples of supercapacitor yarns, and different other yarn technologies. One of the challenges with that is the resistance along the length of the yarn can become increasingly limiting, shall we say. And getting the yarns then to mechanically survive the weaving or knitting process to convert the yarn into the textile can also be challenging. We took this approach purely because our background is in printing generally, and we've been printing active materials since the 1980s, normally high temperature materials, and we very foolishly thought, why don't we just work with polymers on textiles? We tried to miss plastics out entirely and went straight to textiles, and that was quite painful. But Yeah, I think so. We've just taken the view of trying to just work with any textile. So all the technologies here will work with any standard textile. Yeah, there is definitely the option to do the yarns, and people have done that. In fact, I'd say most publications, most research are on yarns.
Actually, I have a just question. If you, I wonder whether you can comment on the washability challenges coming from the washability of wearable textiles.
So that's the question everybody asks, and it is a challenge. So when we've got the electronics to survive 50 washes, standard wash cycles, etc., it's a significant achievement. I think it's not so much the liquid environment; it's just the pure physicality of the wash process with the unfolding, etc. So yeah, it's we do have a washing machine. Everything we do, we just try to do the wash tests, etc. And with varying degrees of success. So yeah, it's part of the standard sort of testing process.
Thank you very much. And let's thank the speaker again. Is the speaker in the room? Okay. If not, I think we should move to the next in line, who is from Vincenzo Pecugno, Suzhou University in China, on optimization of all transport layer in solution processed